Hello again. Welcome to a little video segment that I thought might be helpful for you to better understand the physics of friction forces and how coefficients of friction relate to that. It's described fairly lengthy in the tutorial, but I thought a little demonstration might be helpful. And so what I've done here is I've made a very short video segment that you'll see on the next slide that you can play and replay and slow down, and I'm going to use that to describe just what exactly happens as an object on a surface is pulled, and then we'll see what its subsequent motion is. So you can, as usual in these videos, play and replay as much as you need to maybe better understand the concepts behind everything. What you see here is a short video clip, about 15 seconds long, showing a 6.5 Newton block that I found in my cabinet, and what happens when I pull on it while it's sitting on my desktop. So you'll notice a scale, a small spring scale that measures in newtons, and if you look closely you'll be able to read the numbers. The Newton scale ranges from 0 up to 2.5 newtons, and so I was able to pinpoint some of the key measurements as I pulled on the block, and I'm going to use that to describe what we know about the coefficients of friction between the block and the table. So you can play the video and replay as necessary, and then if you need to, go back as I work through some of the math to see that you're seeing on the video what I'm describing. One question we might ask about this is, what would a force diagram or a free body diagram look like for the block as it just sits on the table and before it's pulled? So here's a situation where we could draw the block pretty easily as a square, and then, as I've been doing in class and you've been mopping about, you just ask yourself, alright, what is able to exert a force on it, either at a distance or by making direct contact? And we always have the one force that's able to be exerted without direct contact, and that's the force of Earth's gravity. And since I know what that number is, I've got it marked on the block, I'm going to go ahead and include that on my diagram, because that is marked on the block as 6.5 newtons. The way I found that was I took the mass, which you would maybe notice is also written on the block, about 661 grams. I converted those grams to kilograms, and then I used this key relationship, one of what I call the key 3, to figure out what the force of gravity, or the weight of the object, is. So I knew its mass in kilograms, and I knew we were here on the surface of the Earth, where every kilogram gets pulled with 9.8 newtons of force. So I say 9.8 newtons per kilogram, and that tells me the weight in newtons. So we could call it the force of gravity, or we can just call it weight, more familiar. So in addition to the force of gravity, we obviously have contact with the table. We call that a surface, and every surface pushes with a normal force. Now, what do we know about the normal force here? Well, because we know that the block is not accelerating up or down, that tells us that we have to have balanced forces up and down. As much down we have to have up. And in this case, there's only one up and one down. So putting those two ideas together, the fact that there's only two forces and they have to be balanced, tells us that this normal force is also 6.5 newtons. Now, what other forces do we have? Well, while the block is just sitting on the table, it was not being pulled by the scale, so I'm not going to include a force from the scale, what we would maybe call an applied force. And there, of course, is contact with the tabletop, but there also is no friction. It's very tempting when you start a discussion about friction to want to draw a friction force every time you have a surface. And let me show you here why you can't do that. If you were to draw a friction force, and I'll draw it here in red, And again, we're talking about the block before it was even attempted to be moved. If you draw a friction force and you can't draw any rightward force opposing it to balance it out, then you're going to have a problem explaining how this block is just sitting on the table. Because clearly there's an unbalanced force there, and an unbalanced force would have to cause an acceleration. So the only solution to this dilemma is either to add a rightward force, which can't be because I couldn't think of anything actually pulling it rightward if I'm not pulling on the scale, or we have to get rid of the leftward force. So that's actually the only solution we have, is to say there is no leftward force. So here is the free body diagram for the block just sitting at rest on the desktop. Now in the next slide we're going to look at what happens when we start to pull on the block. If you go back and look carefully at the video, you'll notice that the block did not start to move until there was almost 2.5 newtons of force pulling on it. I registered about 2.4. But at one point on the video, and you might be able to actually stop it in the right spot, you'll see the block with 1 newton of force pulling on it. Now, by virtue of pulling on the block, that does not change anything we know about the vertical forces. We still have the same amount of weight due to Earth's gravity. We still have the same upward equal normal force from the table. But now we would show a rightward force, and I'm not trying to scale these right, but at one point the scale applies a force, so we could call it an applied force from the scale of 1 newton. Again, I just picked 1 newton somewhat arbitrarily because I noticed at one point in the video that the scale did read 1 newton. So what do we know about the other forces? Well, keep in mind that the block was still not moving. What we say sometimes in physics, it was at rest. So we did not see any evidence of acceleration yet. It did at the end of the video, but not yet. So that means that we have to have a force balancing out that scale. Well, what's the only object that can exert a leftward force to balance out the 1 newton from the scale? Only the surface is in contact with it, and so that force leftward from the surface that keeps the block from moving must be static friction. I use a little different abbreviations than he does in his tutorial. I'll say F for force, and then a smaller f for friction, and then a subscript of that for static. And at this point in time, that static friction force must also be 1 newton so that it is able to balance out the force of the scale. Now, notice how the static friction force is adjusting. It started out a moment ago as 0. That was before I was pulling on it. And as I build up more force in the scale, I also build up more static friction resisting that motion. So in a moment here, I might be up to 2 newtons, and the block's still not moving. Therefore, the friction force is up to 2 newtons. Okay? So we're looking at a static friction force that is adjusting itself based on how hard we're pulling on it. Now let's talk about what happens when the block finally breaks free from the surface. So if you go replay the video, you will see the block starts to break free and move right when the scale reached almost full scale. It was actually 2.4 newtons, the best I could see. So I'm going to show this a little bit bigger than I did the other one. So the applied force of the scale, 2.4 newtons. Now what does that tell us about the friction? Well, friction was not able to resist the motion anymore. So we reach this critical point as we pull on it where the friction is just able, I'm going to erase that, it was a little too long, just able to reach a maximum value and get no bigger. And right here is that maximum value of 2.4 newtons. So if we try to continue pulling, the friction force is not going to increase any more than that. So I've reached a maximum static friction force. And this maximum static friction force, now I'm going to add yet another subscript here, always occurs right when we've reached a value of mu. This is the symbol mu, it's the Greek letter M in their alphabet, and that's what we call the coefficient of static friction. Coefficient of static friction. When we take that value and multiply it by the normal force, that tells us the maximum amount of static friction that we can ever have. So the coefficient is just a number. There's no unit with it. When we multiply it by the normal force in newtons, that's when we get the static friction force. So don't confuse a force with a coefficient. They're related, but not the same thing. Now I'm going to remind you of some of the other values that we know. Remember that this block was 6.5 newtons in weight, and we knew then that there must be a normal force from the table pushing up with the same amount, 6.5 newtons. And so we know this value here, 6.5, and we measured this value here, the maximum static friction, could only reach 2.4. And so I can actually calculate the coefficient of static friction just by dividing those. And I'm not going to show the math here, but if you divide 2.4 newtons by 6.5 newtons, you'll get a coefficient of friction of approximately 0.37. And I'm not putting any units on that because the newtons cancel out. So that is a measure of the coefficient of static friction between my desktop and that wooden block that I was pulling. Okay, again, we found that by finding the value of the friction just when the block started to move, and then we put that in for the maximum friction force. Now, you'll notice in the video, once it was starting to move, that friction force was adjusted. And if you go back and replay it, you'll see an explanation of what I'm going to do next. So as I continued to pull on that block, this was the same 6.5 Newton block sitting on the same table. So we still had those two vertical forces. But did you notice that the scale was only applying 1.4 newtons as it was sliding across? Tried to catch that well enough on the video that you could see it. That was as I was pulling it at a steady speed. I played it for a little while so you could tell I wasn't trying to get it faster or slower. So now the scale is down to 1.4 newtons. Well, what do we have to do to finish this diagram? We obviously have to have something else, because if I only have that rightward force of the scale, I'm not going to be able to move at a constant speed. That tells me that we still have some friction opposing that force from the scale, but this time it's not static friction because the block is actually sliding. We will refer to this as sliding friction. I worry a little bit about sliding and static both starting with S. In other textbooks, you'll see this referred to as kinetic friction. Kinetic implies motion. But I'm going to stick with his convention on the tutorial and call it sliding. So how big must this sliding friction force be? Might be a good idea for you to just stop the video here for a second and make sure you could answer that question yourself. How big must the sliding friction force be in order to maintain constant velocity? I hope you can see that would require 1.4 newtons leftward, just enough to balance out the applied force from the scale rightward. So notice that is less than the friction that we needed to get the thing moving. And that's an important property of friction, that's almost universally true. There may be some few exceptions that are a little bizarre, but the friction while something is sliding is less than the friction while it's just sitting there and we're attempting to get it started. So now we can use this same relationship for sliding friction that we used for the static friction, except this time it's not any kind of maximum. This is actually going to be the friction force that is applied as long as this block continues to move. So this mu, this is the coefficient of sliding friction. It's not the same number, the 0.37 number, that we have when it was just sitting on the table. Coefficient of sliding friction. It will be a little bit less than that. We could use the same kind of math that we used before. Since I know that the normal force is still 6.5 newtons, the friction force is now reduced to 1.4 newtons. If I do the math of 1.4 divided by 6.5, I get a coefficient of only 0.22 or thereabouts. So that is the coefficient of sliding friction between these two surfaces. So the key here is to know that between two surfaces there are actually two different measures of the friction. One for the static friction and one for the sliding friction. And those coefficients tell us something about how those surfaces interact, usually how rough or sticky they are. Sometimes it's even a matter of how smooth they are. Super smooth surfaces like two plates of glass sitting on each other have a very high friction because the molecules of the two glass plates are just so strongly attracted to each other. You might remember in biology class trying to separate a couple of microscope slides. Very difficult to do with your fingers. So the sliding attempt here gives us a measure of this sliding friction coefficient. Alright, we'll do one last thing here, and that is something that I couldn't really show in the video, but what happens if I just drop the scale and I let the block do its own thing? Well, let's start, as I often do, with a diagram of what this block would look like once I let go of the scale. Now, we don't change anything about the gravity force or the normal force by virtue of what we do with the scale. So those will stay in their same values of 6.5 newtons. But I can no longer draw a force from the scale because even though I couldn't unhook it, by letting go of it, it no longer exerts a force. But does that mean that friction goes away? And something you may have missed when I said it on the last screen was, as long as these surfaces are sliding across each other, we will have sliding friction opposing that motion. So we still have a friction force. Which way? Well, because the motion was rightward, the friction force is still going to be leftward. And this is sliding still. But we don't have a rightward force, even though the block is still moving rightward. I think a misconception might be that letting go of the scale would instantly stop the block from moving. But as we'll show here in just a second, it'll take a little bit of time to get that block to stop. This is the idea behind the idea of inertia is, when a block is half a kilogram, that's a measure of its inertia, how it likes to maintain the motion that it has. We're only going to change the motion because we have a force opposite the way that it's moving, and that will cause it to slow down over time. So now we have one of the first cases of an unbalanced force. I think this is the first example in the entire video of an unbalanced force. So now we can use Newton's second law to figure out how much acceleration we'll have. I'll write Newton's second law in the form that's going to be convenient for us here. That's F net divided by the mass will give us the acceleration. F net is just a fancy name for how much unbalanced force do we have. Well, we don't have any vertical unbalanced force. Those have stayed balanced the entire time. But we have the same 1.4 newtons of friction that is not balanced by anything in the other direction. So we would say 1.4 newtons of friction force exerted on a 0.66 kilogram block. Now you notice on the block in the video you saw it marked in grams. Well, 661 grams is 0.66 kilograms. And so we run that through the calculator. We'll get 2.1 meters per second squared for the acceleration. Now what is the direction of that acceleration going to be? I don't have much space here, so I'm just going to write it. This is leftward acceleration. The direction of the acceleration is always in the same direction that the unbalanced force is. So leftward acceleration for a rightward moving object, and to show rightward moving object here, you might put these little motion tails in. I'll do it in red so they don't blend in with other stuff. That always means getting slower, which is obvious. That must be what the block would do once we let go of the scale. So that's about the last thing we could do until this thing comes to a stop. And once it stops, then we're back to where we started, which was the block just at rest on the desktop. So I know this has been a little lengthy, maybe lengthier than I expected, but we've been through a lot of things related to friction, and I hope I've shown you some of the key relationships between static friction versus sliding friction, how those are used when you incorporate them into free body diagrams, and then how we use the key three relationships. That's the FG, the FNet, and the FF equations. We use them throughout the video. Equations 6, 7, and 8 on your reference sheet, and how those are used all together to completely describe how these forces relate to the motion. So anything more that you would need, of course you can come and run through things more with me in the classroom.